Good afternoon, everyone. Today, I'm going to present a system design of a scalable payment gateway using Razorpay as the reference architecture. Digital payments have become a critical part of modern commerce, where even a small transaction requires high security, very low latency, and extremely high availability. A payment gateway is essential to act as the bridge between the customers, merchant, banks, and payment networks. In this presentation, we will look at how such a system can be designed using microservice caching, messages, queues, database, and a security mechanism. We will also understand how a system handles the millions of transactions while preventing the failures, duplicate payments, and inconsistent financial records. Before designing the architecture, we first need to understand what the system must achieve. Functionally, the gateway should create payment orders, process payments, support multiple methods such as UPI, cards, net banking, and wallets, track transaction status, right? And the process of refunds and finally settle payments with the merchants. But functionality alone is not sufficient. From a non-functional perspective, the system must provide, right? I mean, uh, it's like uh, before it's like designing this architecture, we first need to understand what the system must achieve, right? The functionality gateway should create a payment orders, the process payment of support with multiple methods as UPI, cards, net banking, and the balance and the transaction status as the process refunds, right? And but the functionality alone is not sufficient. From a non-functional perspective, the system must provide a requirement, right? On particularly the important requirement is independency. If a customer accidentally sends the same payment request twice, the system must never charge the customer twice. So that the architecture must balance the performance with the financial correctness. Now let us look at the overall architecture. The system follows a microservice, right? Approach where each major responsibility is handled by independent servers. The API gateway act as a single entry point and performs the routing, validation, and rate limiting. The authentication service validates the merchant's credentials and the permissions. The payment services manages the payment lifecycle, while the transaction service maintains the transaction record and the audit information. Behind these services, we have Redis for the caching and the dependency, the Kaifa for asynchronous communication, and PostgreSQL for reliable transactions storage. The load balancers distribute the traffic while monitoring tools such as Prometheus, Grafana, and Jaguar help us to observe the system in the real time. Let us follow a payment from beginning to end. First, the customer clicks Pay Now. The merchant creates an order through the payment gateway and receives a unique order ID. The gateway authenticates the request and validates the merchant credentials. The payment service then selects the appropriate payment method such as UPI or card and sends the transaction securely to the bank payment network. The bank authenticates the customer and returns a signed response. The transaction service then updates the payment status from pending to success or failure and the records of the audit information has been done. Finally, the Kafka triggers an asynchronous webhook to notify the merchant while the customer receives the payment confirmation. This separation keeps the payment path that fast and traceable. A payment system must be prepared not only for the normal traffic, but also for sudden traffic spikes such as festival sales or major online events. The architecture addresses these use of horizontal scaling, the load balancing, and the caching. Stateless service can be settlement from the main point, right? For the reliability, the system uses the exponential back of retires, circuit breakers, impedance of keys, and dead letter queues. The target metric shown here are 99.9% are available. P99 latency of 500 milliseconds and the ability to handle is approximately 10 times than the normal traffic. Security is one of the most critical aspects of the payment system design because we are dealing directly with financial information. The architecture uses TLS 1.3 for encrypted communication and tokenization so that the sensitive card information is not stored directly. API authentication, PCI DCS compliance, fraud detection, and the secure input validation provide the multiple layers of protection. Equally important is for failure handling. For example, if a bank times out, the system retires safely and may move the transaction into the reconciliation. If the same request arrives twice, the idempotency key will make this to disable and it will verify the bank status, right? The fundamental principle is simple: retry safely, maintain the transaction state, and never double charge the customer. To summarize this presentation, the architecture demonstrates how the distributed system principles can be applied to build a payment gateway that is scalable, secure, and reliable. The scalability comes from stateless microservice and horizontal scaling. The reliability comes from retired circuit breakers and related parts. Security is implemented through encryption, tokenization, and the compliance and fraud detection. Consistency is maintained through the abdominancy, ACID transaction, audit logs, and reconciliation. These were important lesson for the system designers to design for a failure from the beginning. Okay, therefore, to summarize, we have explored the complete design, right? We have explored the complete design of a production grade payment gateway, from identifying a functional and the non-functional requirements to designing a microservice architecture, understanding the end-to-end transaction flow, and implementing the scalability, security, and fail handling mechanism. The key takeaway is that the payments system is not simply about transferring money quickly. It must transfer money correctly, securely, and reliably, and consistently. Even when the individual components fail, these principles scalability in this modern world would mean designing any modern distributed financial system. Thank you for your time and attention. Thank you all.